Hi, in this video we're going to finish our discussion of gradients in terms of just finding them, computing them, and using them to get directional derivatives. We're just going to start off with a bang and talk about a 3D gradient. So if you had a three-dimensional gradient is coming from a four-dimensional function. If I have a four-dimensional function, a function with three inputs, right? If you see three inputs, it's outputting into a fourth dimension, so a 4D space. If we have a function with three inputs, the gradient will be three-dimensional. I was not misspeaking for once. Oops. So we're just going to stick all three of those components on top of each other, or to go back to IJK notation, again, fx in the I direction, fy in the j direction, and fz in the k direction. Those are the three partial derivatives. Notice again, f of x, y, z, I'll write down what I was saying, is a 4D function because we need one for the output, and it gives rise to the gradient of f is a 3D vector. Now, it's a vector function. Thinking about chapter 13, perhaps it's a very important vector function, and that's why you might see it a lot once we get to chapter 16. So, a brief example of this. If you have f of x, y, z, x plus y over x plus z, can we find the gradient of f evaluated at 1, 2, 3? Can we find this gradient evaluated at the point 1, 2, 3? Pause the video, find these partial derivatives. 3, 2, 1. Partial derivative f sub x, f sub y, f sub z. If you were confused what you were supposed to be finding, I suggest you pause the video now, take that hint, and move on with it. One of these is a lot harder than the other. One of these partial derivatives is harder than the other because only one of these requires the quotient rule. Because only one letter is represented in both the top and the bottom, and that letter is, of course, x. So, if I did all my work carefully, I would get the low function, which is x plus z, times the derivative of the top, which is just 1, minus the top times the derivative of the bottom, all over the bottom squared. Sorry, I'm writing on a slant. And if I check that top out carefully, I'm getting z minus y over x plus z squared. There's my fx component. My fy, my y partial derivative, is just the derivative of the top with respect to y, 1. The z component's much more annoying, but it also does not have to involve the quotient rule. You can master it if you just think about it as I need to take the derivative of the bottom and keep the top constant. So I'm talking about negative x plus y over x plus z squared. Maybe I want to write it like this before anyone freaks out. So those are the three components. I combine them to get the gradient of f to be, I'll use bracket notation here just because I feel like it. Whatever notation you want is fine. As long as it's correct, it will be okay. What does this represent? This still represents the direction I should go in 3D space in order to maximize the change of that fourth dimensional variable, okay? Now, again, I'm not asking you to visualize some sort of 4D surface. That's not easy for our brains. But let's say the fourth dimension was heat. That F was measuring the heat of a space, of a region of space. And I wanted to make sure I lowered my heat as fast as possible. What direction would I move? I would move in this direction, given any coordinate, right? So this would help you in navigation, theoretically. I don't know. Just that's my image for always whenever we're talking about a 4D function, where we're talking about the input is a coordinate in space. Maybe it's the mass of that space. Maybe it's the gravitational pull of that space or the force. Well, the force is a vector, but okay, like, right? It's some measurement of that 3D space, of that point in 3D space. And if we want to maximize the change we would get out of that variable, this is the direction I would travel. So at the point 1, 2, 3, I would get the vector, specifically 3 minus 2 over, 4 squared, 16, comma 1 over 4, comma negative 3 over 16. Just change that to a 1. That looks bad. 1/16, 1/4, negative 3 also looks bad. 16ths. That would be the direction I would move in that three-dimensional space in order to, get away from the solar flare or whatever. Whatever's making, whatever quantity I want to change, that's the direction I would move to change it the fastest. Okay. I want to do more practice problems just to make sure this idea is pretty set. So let's go back to 2D Town. Find the directional derivative given f of xy equals x squared plus y squared plus 1 to the 1/2 power. I could have written that with the square root, making it nice for you, making sure we understand it's going to be the power rule. At the point 1, 2, our favorite point, in the direction of, yikes, that's not an I, in the direction of my vector 3i plus 4j. Okay. Now, can you do this the way we did it in our very first video? Yes, sure. But probably what you should be doing, depending on how this question goes, right? You don't know where it's going to go from here. If it's a multi-part question, you might want to start off by finding the gradient at the specific point. Why do I want to find it at the specific point? Because I want to avoid the messiness with the x's and the y's if possible. Now, there's no shortcut here. Sorry, this is like f of 2, 2. You need to do derivatives in the order you've always done them, which is first find the gradient of f without plugging in, and then plug in. So, on your paper right now, find the partial derivative with respect to x and the partial derivative with respect to y. 3, 2, 1. With respect to x, I'm going to get 2x divided by 2 x squared plus y squared plus 1 to the 1/2, all in the bottom. And for the y, it's a similar situation. Oh my gosh, that's what happens when you copy. 2y over pretty much the exact same thing with respect to the y's. Okay? Now, I might notice those 2's can cancel, huh? So the gradient f is going to be x over, can I write it with a square root? Will that freak anyone out? X squared plus y squared plus 1 in the I direction plus y over the square root x squared plus y squared plus 1 in the j direction. And more to the point, the gradient at the point 1 comma 2, 1 over root 6 root 6. Gross. Plus 1 over root 6. Sorry, I hat and then j hat. Step 2. We're going to find u. Now remember, finding u is mainly important because some students will forget to resize u to change the vector given into a unit vector. You should be able to tell that's not going to be a unit vector. That vector is too big in each component. Unit vectors are tiny little things that touch the unit circle. The unit circle only has a radius of 1, and this x coordinate is 3 out. That's how easy it should be to tell this guy is not going to be a unit vector. It also is not labeled with the letter u. The magnitude of v, you should be able to find that. And then u should be the v vector divided by the magnitude of v or multiplied by the reciprocal. Find those for me, please. 3, 2, 1. The magnitude of v, so 3, 4, 5 triangle. And so our unit vector is 3/5 in the I direction plus 4/5 in the j direction. Our final step is to use our formula, our knowledge, our know-how to say this guy, all put together, is my gradient evaluated at the point times some unit vector. And when I say times, I'm sorry, I could have been more specific. Dotted with, dot product with the unit vector. So we're talking about the vector. Yeah, I'm going to write it as bracket notation, even though I've been avoiding that up until now because I just like doing that with a dot product. I don't like worrying about the I and the j, and I don't know, I feel like if I use parentheses and I and j, I would distribute or something, and that's not right. Dot product is simple. It's 3 over 5 root 6, multiply those, plus 4 over 5 root 6, 5 root 6, which is 7 over 5 root 6. You could rationalize that, but there's absolutely no need to. There you go. Let's do 1 or 2 more examples. Let's do 1 or 2 more examples. F of xy, oh man, f of xy equals x e to the negative y. And we're going to ask you to find the direction vector. Sorry, the directional derivative. I think I mispronounced it every single time I said it. At the point 2 comma 0 in the direction of the line from P, that same point 2 comma 0, to Q, the point negative 1 comma 2. Okay, so first step is still going to be the same. And this should be easier. Well, step 1. Okay, find the gradient f of xy. Step 2 is also the same, which is find the unit vector. You should be able to handle both of these on your own by now. And that means step 3, the profit step, is use that formula. 2, 0 will equal the gradient evaluated at 2, 0, dotted with the unit vector. Pause the video and try to find as much as you can, unpausing the video when you need hints. 3, 2, 1. The gradient vector, if you're careful with your differentiation, should have been the vector, let's do it, e to the negative y, keeping the x as a variable and treating e to the y as a constant, which just says like x times 5 to me, minus, now we're holding the x as a constant and taking the derivative of the exponent. The chain rule component is what gives me this negative. And so at the point 2, 0, we're talking about I hat minus 2j hat. That's not a unit vector, just to be clear. The gradient vector does not have to be a unit vector. Okay? How about u? This is where I would have expected some students to get stuck. Obviously, u is going to have that same equation we have been using. But how do I get v to begin with? They didn't give me v. I hope you didn't just turn one of these into a vector. There's an order here. We have to go from p to q. So we need to subtract p's coordinates from q's coordinates. So we're talking about negative 3, 2. The magnitude of v is going to be 9 plus 4, or root 13. And so the unit vector I would use is negative root 13, in the I plus 2 over root 13 in the j component. Putting it all together here, I'll do it with the parentheses. I'll dare myself. Now remember, one thing I've recommended before, you can leave that root 13 factored out like this. Okay, and then you can do the dot product. I'm not going to try to mess this up though. I can leave plenty of space and do it this way. And I get negative 3 root 13. These two, 1 times that, easy peasy, minus 4 over root 13 from the j component. I'm not writing j and I anymore. They're gone. This is just, I'm saying from the j. That's how much change the j contributes. Or negative 7/13. Root 13. Negative 7 divided by root 13. Keep forgetting to say the root. One more example of this format, but let's go up to 3D. Trying to give you guys lots of practice. The gradient's a very, very important idea. Given f of x, y, z equals the square root of x, y, z. Find the directional derivative, the 3D directional derivative, it's the same formula, in the direction of the line through P 4, 2, 2 and Q 6, negative 2, 6 at the point 4, 2, 2. Nothing can really make the directional derivative that much harder. Okay? We're just going to do the gradient. The gradient is still partial derivatives assembled into a vector. Find the 3 partial derivatives of this function to find the gradient, and then we're going to plug in 4, 2, 2. Just to be clear, it's because they say at this point. I know it might be confusing. In the last example, this happened too. I don't think I said anything about it. There's 2 points you could use. We're using this one because that's where we're doing the derivative at. We're finding the slope at this point. So, sorry, not that. You're going to find 3 partial derivatives, and it should be pretty similar. Do at least one of them. 3, 2, 1. I've alluded to the idea of symmetry here a few times. What am I saying when I talk about symmetry? They are all multiplied together. They are all in the same exact spot. They are all under a square root. If someone came along and switched these letters, would it have any effect? No. It would just be a relabeling. So we can exploit that fact. The derivative, in fact, is just going to be just such a relabeling. That's one reason I'm able to do this so quickly. Because I can recognize when these functions are symmetric in that way, where it's just a relabeling of who's where. Now, while they are symmetric, that does not mean they're all going to evaluate to the same thing. So the gradient of f in general, the gradient of f at any point, the max direction at any point, is assembling this into a vector. On a test session, on a test, I would definitely notice whether you put the i's or whether you put brackets or whatnot, because it's a very important piece of calling something the gradient. X, Y, Z. And when we do the gradient at 4, 2, 2, lots of mistakes. I'm getting 4 over 2 root 4 times 2 times 2 is 16. And the I plus, now we're going to change it up, 8 over 2 root 16 in the J plus 8 over 2 root 16 in the K. I forgot a K right here. Please pay attention. You need a K. Just like I was just saying how you can't have to get all 3 of them. We'll notice if it's a derivative or not. We'll notice if it's a vector or not. That's 2 over root 16. Sorry, let's be clear. Root 16 is 4. It's 1/2 in the I direction plus 1 in the J direction plus 1 in the K direction. Okay. 2. Getting U hat, we need to start with a V hat or V arrow. If you didn't try this yet, please pause the video now and give it a shot. 3, 2, 1. My V direction should be 2, -4, +4. With the magnitude of that vector being the square root of 4 plus 16 plus 16, or the number 6. So altogether, U hat is 1/3, -2/3, +2/3. And now we just need to take a dot product to assemble all of this into a final kind of answer. At the point 4, 2, 2. Again, that at the point is why we have the gradient where we did the gradient. The directional derivative contains that other point's information. We didn't lose any information here. We're just using it carefully. So I'm talking about 1/2, 1, 1, dot with 1/3, -2/3, +2/3, 1/6, minus 2/3 plus 2/3, which is 1/6. Very small rate of change, I guess. I mean, relative to what, but. Okay, so that's the theory of how we use these gradients, especially to get partial derivatives, especially get to directional derivatives. I guess I should be more specific. And just remember that this can help you find the direction of the maximum rate of change. Okay, and what would that maximum rate of change be? It would be the size of the gradient. Just the gradient, no u in that case. Those are the most important things. Make sure you practice this stuff on the homework, and I'll see you in the next video where we'll finish our discussion of why the gradient's so helpful. Bye for now.